Hello and welcome to College Physics 1, Lecture 10, Solving One-Dimensional Motion Problems. So, the big challenge when solving a physics problem is to translate the words into symbols that can be manipulated, calculated, and/or graphed. This translation from words to symbols is the heart of problem solving in physics. Ambiguous words and phrases must be clarified, the imprecise must be made precise, and you must arrive at an understanding of exactly what the question is asking you. And this can often be more challenging than you might suspect. So, to begin, identify important elements of the problem and collect information. It is tempting to jump right into solving the problem, but a skilled problem solver will spend most of their time in preparation. So what do we mean by this? Well, before we jump into a bunch of different examples for this lecture, let's set up a problem-solving strategy. In other words, a list of steps that will allow us to work out these problems. So step number 1 says draw a picture, such as a motion diagram, and/or a graph. That being, say, a position, velocity, or acceleration graph. But note that I tag this as being only recommended. I don't typically do this myself, this step, unless it's for a particularly complicated problem. But that said, if you're a visual learner, a lot of times you'll gain extra information or comfort if you have a visual aid. So this is only recommended. The rest of the steps, for my students' purposes, I do require, especially number 2 here. Step number 2 says, collect necessary information by writing out your known values and those you must find. So you'll see what I mean by this in just a minute when we jump into our examples. Step number 3, do preliminary calculations such as unit conversions. Up until this point, you may have been able to get away with doing unit conversions at the end once you get your answer, but these problems become pretty complicated. And because of this, it is almost required, it's imperative that you do your unit conversions before plugging in all your numbers into these long and complicated formulas and maybe having an issue down the road. So just get kind of situated in the mindset of doing these conversions before you actually work out the problem. So that, of course, then brings us to step number 4, which says solve the problem. This is, of course, vague because how you solve the problem depends on the problem itself, but at this point, you find the equations you need to work with and attempt to solve. Once you have an answer, or believe you have the answer, check it for proper units and significant figures. And then, very importantly, you could be able to ask yourself, does this answer make sense? Now, this is generally vague because, you don't necessarily always know what the exact answer should be, but you can reason that. Just for example, if we're trying to solve for the speed of somebody walking, and you get 1,000 meters per second, obviously that can't make sense. So you should be able to ballpark whether or not your answer makes sense, for some of the simpler problems at least. Okay, so in our last lecture we came up with our 3 equations for motion at constant acceleration, and now we have this problem-solving strategy. Let's take everything and apply it to solve 4 different examples throughout this lecture. So here are those 3 main equations again, the equations of constant acceleration. We will refer to these quite a few times throughout this lecture. So, example number 1. As you drive in your car at 15 meters per second, you see a child's ball roll into the street ahead of you. You hit the brakes and come to rest in 1.5 seconds. How far does your car travel as you brake to a stop? So, step number 1 says perhaps draw a picture. Again, for simpler problems, I'm not going to do that, especially for the sake of time and space on the screen. So that will lead us to step number 2, which says to write down our known values and what to find. So right at the beginning of every problem, I always do the following. I write down the word known and the word find. And I leave space so that I can fill in our information. So the problem has a lot of words, but there are some numbers embedded within it that we can extract. So to do this, take a look at what the problem says. So we are saying we are driving at 15 meters per second. Okay, well that's a value we know, but what is that value is the real question. Well, it's saying we're driving at 15 meters per second, so that's certainly a velocity. And I'm using an x subscript since it's horizontal motion. But you have to ask yourself whenever you get a problem like this, is this my initial or my final velocity? Well, read the problem a little bit. So it says you're traveling at 15 meters per second. You then hit your brakes and come to rest. So you are starting with an initial velocity of 15 meters per second. You then hit the brakes and come to rest. So this is actually a key point here. We actually know our final velocity as well. Even though it doesn't explicitly give us a number, it says that we come to rest, in other words, brake to a stop. Well, if you're at rest or you have stopped moving, your velocity is 0 meters per second. So be careful. A lot of times you will have a number hidden in the words of the problem. Okay, well, we also are given the fact that we come to rest in 1.5 seconds, seconds being the unit of time. So we know our time interval here is 1.5 seconds. The last point to make is the fact that you should be able to establish that you start at the origin. You get to define that. So we're going to always say, unless told otherwise, that we start at a position of 0, the origin. We define our starting point to be the origin. So this is very common in horizontal motion problems. We just say we start at 0, so things are pretty straightforward from there. Okay, I believe that is all we know, and so we can write down what we're looking for now. The problem asks, how far does your car travel? So, this means one of two things. We're either looking for where we end up, in other words, the final position, or, depending on how you think of it, this is our displacement. Right? How far you're traveling is how far you have been displaced. So I say x final or delta x for good reason. Again, remember, delta x means final minus initial. Well, our initial position is 0. So delta x is technically just x final minus 0, so it's really the same thing here. So I'm just trying to make it clear that either of these are acceptable to find. It is the same thing. So that was step 2. Step number 3 says to do preliminary calculations. Well, we're lucky in this case. Everything is in base units of meters and or seconds, and so we don't have to do step 3. We don't have any unit conversions. That then takes us to, of course, step 4, solve the problem. So at this point, what you should do once you have your knowns and your finds, and you're ready to solve, you look at those 3 main equations and figure out which one applies here. So, let's go back and look at these. We're looking for a position, x final, or the displacement, delta x. Recognize that in equation 2, we do have the position x final, and in equation 3, we have a delta x. So that's good. We could technically, in theory, solve either of these equations then. But realize that equation 1 does not have a position or displacement in it, so there's no way we could use equation 1 to solve, right? If we're looking for x final or delta x, there isn't one here. equation 1 cannot possibly help us. So we've ruled out one equation. At this point, we can ask ourselves, which one of the two do we use? Well, we know x initial, we know the initial velocity, and we know how long this takes. But we don't know the acceleration, ax. Well, what about the third equation? We know the final velocity, we know the initial velocity, but again, we don't know the acceleration. So when you get to this point, you could be stumped, right? Because it seems as though none of these equations will work for us to solve this problem. So either I wrote down the problem wrong and I'm just giving you something that's impossible, or it's just an indication that you have to find the acceleration first, and then you can solve using one of these equations. So, we're looking for a position, which means we can't use that first equation. However, both the second and third equations require us to know the acceleration, so we simply have to find the acceleration first. So we can use the definition of acceleration to do this. Acceleration, by definition, is the change in your velocity over the change in time. Right? And note, I'm writing down my thought process, so when I say we're looking for a position, blah, 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 you don't have to do that as a student. I'm just doing this so you can have it in words, so I'm relaying my thought process to you. So anyway, so let's solve for the acceleration. So remember, delta means final minus initial. So we have our final velocity of 0 meters per second. Let me fix that. We come to rest at the end, so it's our final velocity that is 0. Okay, pen. 0 meters per second minus our initial velocity of 15 meters per second, all divided by delta t, which was 1.5 seconds. This will give us a negative 10 meters per second squared. Now you might be asking yourself, is it okay to have a negative acceleration? The answer is yes. We always assume that we're moving to the right, in other words, the positive direction. So if we're moving to the right in the positive direction, but we're slowing down, well, remember from our previous lectures, if you're slowing down, that means acceleration by definition points in the opposite direction of your motion. So if we're moving to the right, that means our acceleration points leftward, which is the negative direction. Anyway, so we now have our acceleration. So when we go back to our equations, we can now fill that in. So we can actually use either the second or the third equation to solve this problem now. So we just have to choose whichever one we prefer. Now, even though equation 2 looks longer and more complicated, personally, I view it as being the easier one to solve. Because we're looking for the delta x down here, which means we would have to rearrange this equation to solve. But in equation 2, all I have to do is plug directly in and solve for x final. So I don't have to do any rearranging, which means there's less room for error, if you ask me. So I'm personally going to choose equation 2 to solve this problem. And again, you don't have to. You can choose equation 3 if you'd like. In theory, as long as you solve everything correctly, you'll get the same answer. Oops. So let's go ahead and solve this. Now, one thing to note that I do require, and this is important, you should always write out the equation in full before plugging any numbers in. So notice I'm writing down the equation as it was on the previous slide without any numbers plugged in. Okay? So the reason you do this is important, so you don't get the equation confused. If you're plugging in numbers immediately without the equation shown, you have more room for error. So I require my students to always write out the equations that you use in full before you plug numbers in. So that said, let's do exactly that and plug in our values. We start at an initial position of 0 at the origin. We have an initial velocity given to us as 15 meters per second. the time interval was 1.5 seconds plus 1/2 the acceleration that we just solved for of -10 meters per second squared, and the time again, 1.5 seconds, quantity squared. Don't forget that square. A lot of times in a stressful environment like a test, students will forget to do the square. Granted, you get partial credit, so it'd be only like a point off, but in physics, every point matters. So you plug all this in, and you should get roughly 11 meters. So it takes you 11 meters to brake to a stop, so hopefully this child's ball is further away from that. Unless you really don't like the kid and you decide to run the ball over, but that's beyond the scope of the class. So, okay, so this is our first example. I understand it can be a lot to take in at first, so that's why I'm going to spend the time to do 3 more with you. So let's get some more practice in and hop over to example 2. Again, I'm going to use these equations, so I pull them back up. Example 2. Spudd Webb was one of the shortest basketball players in the NBA. However, he had an impressive vertical leap. He was able to jump 110 centimeters from the ground. In order to jump this high, with what speed would he have left the ground with? So, first thing to note, this is vertical motion, so we're going to switch our subscripts from x's to y's to indicate that it's vertical. So let's go ahead and try to write down some of our known values. So we are only given one number in this example. It says 110 centimeters. So again, this is an interesting point where you can differentiate between initial and final position or displacement. So you could write displacement delta y is equal to 110 centimeters. But I like to be personally more specific, so I'm going to write down y initial and y final. Only by personal preference. You can again write delta y equals 110 centimeters. But I like to be as specific as I can. So let's try to say what his initial and his final position are. Recognize that we're only focused on his jump upward, not what happens as he comes back down, right? Because it's asking for the speed that he leaves the ground with so that he can get to the maximum height. So we only care about what's happening going upward. So we can say he starts at ground level, so he's starting at 0 meters. He then jumps 110 centimeters above that. In other words, 1.1 meters. Okay, so this is the same again as writing delta y equals 110. I'm just being more specific in case I need to be. So that's the only value given to us. But we do actually still know 2 more values. So think about what's happening, right? First of all, he's jumping through the air. And if you recall from our previous discussion, an object moving through the air, assuming no air resistance, is considered to be in free fall. And in free fall, all objects have the same acceleration. It is the acceleration due to gravity, or negative 9.8 meters per second squared. So this is true for any object in free fall, like Spudd Webb is while he's moving through the air. So we have the acceleration. We also have one more value, and I'll give you a hint. It's a velocity. Now this is often a big point of confusion for students. Do we know his initial or his final velocity? So because he starts, if you think about it, standing on the ground, a lot of students would say he's starting with an initial velocity of 0. But you have to be careful. We're focused on his motion, not him standing still before his motion. That's irrelevant to the problem. he has to have some initial velocity, otherwise he wouldn't leave the ground. He would just be stuck on the ground. So he has an initial velocity. We need to find that. But what he does have is a final velocity at the top of his motion. Right? At the very top of his motion, when he reaches his highest point, he comes to a stop before he falls back down. Right? You jump upward, you slow down, slow down, slow down, come to a stop at the top for a split second, and then you start falling back down. So his final velocity, that at the top of his path, is 0. With that, we can write down what we're looking to find. It says, with what speed would he leave the ground with? Well, in that case, we're looking for the initial velocity, Vy initial. The speed he initially left the ground with to jump to this height. So that is step 2 of our problem-solving strategy. Step 3 says to look for any unit conversions. Technically, I did a very rapid one in changing our centimeters to meters by dividing by 100. So aside from that, we don't have anything to do for step 3, so we can go right into solving the problem. So again, at this point, we look to our 3 big equations. Well, we have one really important thing that is missing, which will tell us exactly what equation to use. In this problem, realize we do not know the time interval, delta t. We have no information about how long this jump takes. Well, if we don't know delta t, we can't use the first equation to solve because it requires us to know it, and we can't use the second equation to solve because it requires us to know it. So that should indicate we probably have to use equation 3. It is independent of time. And so if we're looking for the initial velocity, well, we know the final velocity, we know the acceleration, and we know the displacement of Spudd Webb. So we can solve this equation. So we don't know the time interval, so we know we must use the third equation. So let's write down that third equation, again in full, without any numbers plugged in first. Vy final squared is equal to Vy initial squared plus 2 Ay delta y. Now, what you should also get used to is rearranging the equation before you plug in numbers as well. It's probably going to seem tedious, but it again helps to eliminate possible errors. So you should rearrange first and then plug in numbers. We are looking for the initial velocity here. So what we are going to need to do is subtract this 2ay term to the other side, and then take the square root to get rid of the square. In other words, we should find Vy initial is equal to the square root of Vy final squared minus that 2ay delta y term, all underneath the root. So at this point, all we have to do is plug in our numbers. So we know the final velocity was 0 meters per second. Minus 2 times the acceleration, which is that due to gravity, negative 9.8 meters per second squared, and times the displacement, which is that 110 centimeters or 1.1 meters. Okay, so we just plug in our values here, and we should find that we get 4.6 meters per second as our solution. And there you have it. So I just want to make one point before we move on. We're dealing with the square root. And realize that you cannot take the square root of a negative number. In our problem here, we have two negatives. A negative times a negative, which makes a positive. So we, in this case, do not have a negative number under the square root.
You never should. If you're working out a problem on your own and you get a negative value inside of your square root, you did something wrong in the setup beforehand. So just a quick heads up to my students, I'll pick up on that. And so if you have a negative value in your square root and then you just pretend that negative doesn't exist and just calculate it anyway, you won't get the credit or probably the right answer. So just be careful. If you have a negative under the root, it's a pretty good sign that something was wrong somewhere else. Okay. Well, we have two more examples, and these next two are each going to have two parts to them. So we're going to make it a little bit longer to really flush out these details. So back to our equations and example 3. A fully loaded Boeing 747 aircraft with engines at full thrust accelerates at 2.6 meters per second squared. Its minimum takeoff speed is 70 meters per second. How much time will the plane take to reach takeoff speed? So let's start there and we'll worry about the second half later. Again, I'm not going to worry about drawing a picture, so let's write down what we know and what we need to find. Well, let's again say that we start at the origin. So let's just say our initial position is 0 meters. And notice we're back to using the subscript x since it's horizontal motion. So again, we always assume the horizontal position is 0 because we're defining it to start at 0, the origin. Another easy one is the acceleration, ax. We know this as 2.6 meters per second squared. Now, we have to go through this process again of figuring out if the 70 meters per second that's given to us as a speed is the initial or the final. Right? So we need to know if that's our starting or our ending velocity. And so, what is it? Is it our initial or final? How do we know? Well, be aware that that's the takeoff speed. In other words, that's the speed that you end up at as you leave the runway. So this is the final speed, the speed that we're leaving the ground with. We can assume that on the runway we start at 0 meters per second. Right? You're sitting at the front of the runway. You then accelerate at a rate of 2.6 meters per second squared until you reach your 70 meter per second takeoff speed. So this is the setup for this problem. This is what we know so far. In terms of what we're looking to find, it says how much time will the plane take. So pretty straightforward in this case, we're of course looking for delta t. The second half says what minimum length of runway does the plane require. We're looking for a length. So again, that means either xf, where the plane ends up, or the overall displacement, delta x. So, let's start with the first part. How much time will the plane take to reach its takeoff speed? Let's look at our equations. In this case, we're looking for a time, which means we certainly cannot use the third equation because there's no time in it at all. If there's no time in it, how could we solve for time? So that leaves us with either equation 1 or equation 2. Notice in equation 1, we know the final velocity, the takeoff speed, we know the initial velocity, we start at rest, and we know the acceleration. So we can solve for time. Equation 2, we don't know the final position. We don't know how far we end up. In fact, that's what we're tasked with finding in the second part. So we have to use equation 1 to solve. So that said, let's take our equation 1 and write it down. The equation says Vx final is equal to Vx initial plus Ax times delta t. So in this case, we're looking to solve for the time, delta t, so we have to rearrange this to solve for it. So delta t will be equal to, subtract vxi to the other side, which will give us vx final minus vx initial, and then divide by the acceleration. All right, so this is the equation to solve for time. So all we have to do is plug in our values. We have the final velocity, the takeoff velocity of 70 meters per second, minus the initial of 0 at the start of the runway. All divided by the acceleration, which was given to us as 2.6 meters per second squared. So we have 70 divided by 2.6. With a little rounding, you should get about 27 seconds as our time. So this fully loaded 747 from rest will take 27 seconds, so almost half a minute, to reach its takeoff speed. We now have the other half of the problem to deal with. What minimum length of runway does the plane require? So we're looking for a position or a displacement. So let's look back at our equations. Ignore the x's that are already here. So we could use the position equation to solve for xf. We know the initial position, we know the initial velocity, we know the time it takes now, and we know the acceleration. So we can solve this equation. Or we could also use the third equation to get delta x, since we know everything else here as well. So we can use either, but again, much like the first example we did, I don't really want to rearrange an equation if I don't have to. So I'm going to choose the second equation to solve. Again, you could use either, it's up to you. Write out your equation in full. X final equals x initial plus Vx initial times delta t plus 1/2 ax times delta t squared. So you just have to plug directly into this equation again. We assume we start at a 0 meter position plus the initial velocity, which was 0 meters per second, times the time of 27 seconds. Notice that's all 0 so far. So all that really matters is this last term, 1/2 times the acceleration of 2.6 meters per second squared, times the time interval again of 27 seconds squared. If you plug this in, I forget which way the rounding will go, either to 940 or 950. I think it's 950. So 950 meters. And so there is our solution. Right, so this means that the runway has to be at least 950 meters long. If it's not, then the plane will run off the runway before it can actually take off. So hopefully we have a runway that is at least that long. All right. Well, I warned you, I think, that we have a lot of math in this lecture, and I think you're starting to see that. Let's conclude today's lecture with one more example. Example 4. A heavy rock is dropped from rest at the top of a cliff and falls 100 meters before hitting the ground. How long does the rock take to fall to the ground, and what is its velocity when it hits? So, in this case, let's kind of work backwards compared to the other examples we did. Let's write down what we're finding first. So, it says, how long does the rock take to fall to the ground? That is a time. We're looking for the time interval, delta t. Additionally, it says, what is its velocity when it hits the ground? So that's the final velocity, Vy final. And again, we're back to y's since this is vertical motion. So let's take a few minutes to figure out what we know. And I will say, please pay attention here to my thought process on writing these down. We are again given a distance, 100 meters, which you again could say is your delta y value. But you have to be very careful. And again, I'm going to specify an initial position and a final position instead of writing the delta y. I think this is more valuable. So at this point, students will do one of two things. They'll either say that you start at 0 and then the rock drops 100 meters. And so I'm going to write it like that real quick. This is not my final result, so if you're writing along with me, don't write this. But if you say that you start at 0 meters, you have to be careful, because that means you're starting at 0 up at the top of the building, and then the object falls 100 meters below that. So you would actually have to put a negative 100 meters here for your final value. So I don't personally like dealing with negatives, right? If you don't have to, let's not deal with these negatives. So that's not the way I tend to think about this. So I usually look at this by concluding, like in a past example, that the ground is always our 0 point. I almost screwed that up again. The ground is our 0 point. I always like to think of that as being the case. So that way it's the same throughout every problem. You're always saying the ground is 0. So that means the rock ends up at the ground finally, and you're starting 100 meters above that. So we don't have a negative sign in this case. The problem will still work out the same way, whether you did it the first way or this way, but just be careful, right? And again, I don't like the negative just because it adds more complication into the problem. Why not remove it if we can? Okay. Well, this object, like the Spudd Webb example, is in free fall. It's an object falling through the air, so like any other object moving through the air, it has the same acceleration on Earth due to gravity of negative 9.8 meters per second squared. Right? Anything in free fall has that same acceleration. We also know one of the velocities. So this is another point of confusion for my students. Again, you're only focused on the actual motion of the object from the instant that it's released to the instant it touches the ground. Because it's hitting the ground, students will often say that the final velocity is 0. But that's not true. That's what happens after the motion of the object. We only care about what happens until the instant that it first hits the ground. It starts at rest initially, because as you hold it in your hand and then release it, it starts at rest at 0 meters per second, and then gravity accelerates it downward. It picks up speed, and it actually reaches its highest speed right as it hits the ground. So be very careful about what you choose to be 0 in problems like this. At this point, again, we're ready to solve. We don't have any unit conversions to do. So, what do? Well, we're looking for time, which means we can't use the third equation, which doesn't have time in it. So what about the first equation? Do we know the acceleration? Well, sure, that's the negative 9.8. Do we know the initial velocity? Absolutely, 0 meters per second, because it's starting at rest in your hand. But we don't know the final velocity. So we cannot use the first equation. We must use the second equation to solve. Right? So we don't know the final velocity, and because we're solving for time, we must use this second equation. So again, write it out in full. Y final equals y initial plus vy initial delta t plus 1/2 ay delta t squared. Now, we're going to do something unique here. Recognize solving for time in this equation might look incredibly difficult at first, because delta t shows up in 2 different places in our equation. And to make it worse, perhaps, realize that this is a quadratic equation. You have delta t squared in one term, delta t to the first power in another, and delta t to the 0th power in the third part. In other words, there's no delta t. This is a quadratic equation by definition, which means if we're solving for that delta t, we would have to use the quadratic formula, right? Well, let's do one thing to make this easier and save ourselves from having to use the quadratic formula. Recognize some things in this equation are equal to 0. The final position goes to 0, and the initial velocity is 0. So this whole middle term here goes away because anything times 0 is 0. So this equation actually simplifies because of some zeros. So we can rewrite this as 0 equals y initial, the middle term goes away, plus 1/2 ay delta t squared. Now delta t is only in one place. It is no longer necessary to solve using a quadratic formula. We have saved ourselves some pain. So, we're solving for delta t. To do this, subtract yi to the other side. So we'll have a negative y initial, and then divide by 1/2 ay. Divide by 1/2 times the acceleration. And then because the delta t is squared, we need to take the square root of this. All right, so at this point, we can plug in our numbers. We have a negative initial position, which is a negative 100 meters, divided by 1/2 times the acceleration, which is a negative 9.8 meters per second squared. Now, again, we're using a square root. Watch your negative signs. We have a negative initial position and a negative acceleration underneath. Those negatives again cancel to make sure that we do keep a positive value under the root. This should give you, with your calculation work, 4.5 seconds as an answer. Okay. Well, unfortunately, there is a second part to this, so we still have more work to do. What is its velocity when it hits the ground? In other words, we're looking for Vy final. So, ignore the x's that are already here. We cannot use the second equation because it does not have Vx final in it at all. But both the first and the third equation do have our V final value. We can use either of the two to solve, so let's pick the easier one in equation 1. Right, so we can now solve for the final velocity. Both 1 and 3 will work. Pick the easier one, in other words, equation 1. So we have the equation in full first, Vy final equals Vy initial plus Ay times delta t. We're lucky in this sense that we don't have to do any rearranging. We're solving for that final velocity, so we just get to plug our values in. We have an initial velocity of 0 meters per second, plus the acceleration of negative 9.8 meters per second squared, and the time interval again of 4.5 seconds that we solved for in the last part. Plug this into your calculator. It's basically it's almost 10 times 4.5, so we get negative 44 meters per second. Now you can ask yourselves, does it make sense that we get a negative? Well, absolutely. This is an object that is falling downward. Moving downward is the negative direction, so we actually should get a negative velocity here because we're moving downward. All right, well, that concludes our examples using this one-dimensional motion and these equations that are applied for them. In our next lecture, we're going to take things one step further. We are now going to deal with two-dimensional motion, so something moving along a ramp or perhaps a projectile moving in a parabolic curved path through the air, so that it's moving in both x and y. So, until then, thanks for watching and have a great day.